What if I told you that concrete's biggest weakness is time? But hold on, I'll explain why. Hey there, engineering enthusiasts! Concrete is one of the most widely used materials in the history of modern engineering, and it's probably present in almost everything you see around you. Buildings, bridges, dams, roads, and even on city sidewalks. It is strong, versatile, and moldable, and that's why it has become the foundation of construction all over the world. But what if I told you that despite all this strength, concrete has a silent and inevitable enemy? Today I'm going to show you why concrete's greatest weakness is actually time itself, and how this happens in a slow, gradual, and almost invisible way. But after all, why does time pose such a big threat to concrete? The answer lies in the very chemical process that gives rise to the material. When we mix cement, water, sand, and gravel, a reaction called hydration takes place. It's this reaction that makes concrete harden and become strong. However, it doesn't end in a few hours or days, as many people think. In fact, concrete keeps reacting for decades. And this same characteristic that ensures its strength development can also open the door to future problems. Over the years, the internal microstructure of concrete keeps changing, and these accumulated changes can compromise its durability. But what happens inside concrete as it ages? Concrete looks solid and impenetrable, but the truth is that every piece of concrete has millions of micropores and microcracks that form naturally. Over time, these pores allow external agents to enter, such as carbon dioxide from the air, chlorides present in marine environments, and even rainwater. These elements slowly begin to penetrate the interior of the structure, and that's when the real problem starts. Concrete by itself can actually hold up well, but the big risk lies in the steel reinforcements it protects. But why does the presence of these external agents harm the steel inside the concrete so much? Steel is naturally protected by the high alkalinity of concrete, which forms a passivating layer around the bars. This layer prevents the metal from oxidizing. The problem is that over time, carbon dioxide reacts with the components of the concrete in a process called carbonation. This reaction lowers the pH of the material and destroys the protective layer of the steel. When this happens, the steel starts to oxidize. Rust takes up more volume than the original steel, so it's as if the steel starts to swell inside. This increase causes internal stresses, which end up creating visible cracks in the concrete. As corrosion progresses, entire parts of the surface layer can come loose, forming what we call spalling. But if concrete is so widely used, does that mean all buildings and bridges are doomed over time? Well, not necessarily. The durability of concrete depends a lot on the environment it is in. In coastal regions, for example, the presence of chlorides greatly accelerates corrosion. In industrial areas, where there is a higher concentration of carbon dioxide in the air, carbonation progresses faster. Therefore, time does not act alone. It is only the vehicle that allows aggressive agents to advance, accumulate, and cause damage over decades. But is there any other process besides carbonation that accelerates the wear of concrete over time? Yes. One of the most studied processes is what we call the alkali-aggregate reaction. This phenomenon occurs when certain types of concrete aggregates react with the alkaline hydroxides present in the cement. This reaction forms an expansive gel which absorbs water and increases in volume, generating internal cracks that can spread throughout the entire structure. Over the years, these cracks accumulate, weaken the material, and allow even more aggressive agents to enter. It's a slow cycle, but extremely destructive. But does time only act from the inside out? Actually, no. The climate is also one of the main factors responsible for the long-term degradation of concrete. Regions with constant cycles of wetting and drying or freezing and thawing tend to accelerate these microcracks. For example, when water penetrates the concrete and freezes, it increases in volume, putting pressure on the walls of the pores. Repeated thousands of times over the decades, this process wears down the structure until larger cracks appear. With that, more water gets in, and the process accelerates even more. But isn't it true that concrete gets stronger over time? That's a common question. It's true that in the first few months and even in the first few years, concrete keeps gaining strength due to the ongoing hydration process. But this gain doesn't last indefinitely. After a certain point, the process becomes so slow that it no longer represents a significant increase. From that point on, the degradation mechanisms start acting faster than hydration can compensate. In other words, concrete only improves up to a certain point, then it starts to age. But is it possible to predict how long a concrete structure will last? Yes, and this is something that is widely studied in modern engineering. Large construction projects are usually designed for a minimum service life of 50, 70, or even 100 years, depending on the use and the environment. This calculation takes into account factors such as the quality of materials, concrete cover over the reinforcement, type of cement, environmental exposure, and construction methods. Time, therefore, is not an invincible enemy. It only becomes a problem when the structure was not designed with it in mind. But if time causes so much damage to concrete, aren't there techniques to slow down this process? The thing is, there are, and many of them. Using special additives that reduce permeability, choosing suitable aggregates, applying protective coatings, and increasing the concrete cover over the steel are some strategies. Another modern solution is the use of cements with pozzolanic components, such as silica fume, metakaolin, or fly ash, which reduce internal porosity and increase durability. Most modern structures already use this strategy to avoid problems in the future. But after all, does concrete reach a point where it can no longer be recovered? Unfortunately, yes. When the steel loses much of its cross-sectional area due to corrosion, or when internal cracks reach an advanced level, recovery may become unfeasible. In these cases, it's necessary to reinforce or even replace entire parts of the structure. That's why regular inspections are essential. Concrete may even look solid on the outside, but inside time may be causing damage. In the end, concrete isn't weak by nature. What happens is that it ages, and this aging is inevitable, just like it is for us. Just like any material exposed to the environment, it suffers the consequences of time, water, carbon dioxide, and climate variations. But understanding these processes is the key to building more safely, conducting proper inspections, and designing structures that can last not just decades, but centuries. If you've made it this far and enjoyed the video, make sure to subscribe if you haven't already, leave a like, and turn on the notification bell. And if you find our content interesting, consider becoming a member to help us keep producing content here. And if you're curious to know about the courses we recommend, scan the QR code here on the side or check the link in the video description to gain access to various opportunities to develop multiple skills that will make a difference in your career. And you, have you ever seen a concrete structure that has deteriorated over time? Any cracks, spalling, or rust appearing? Tell me in the comments, because I want to know what you found out there. On the side, there are 2 interesting videos that you need to watch to expand your knowledge and satisfy your curiosity. And if you want to support us, leave your like, subscribe to the channel, turn on the notification bell, and consider becoming a channel member. That's it, engineering lovers. A big hug, and I'll see you in the next video.